Hi everyone, in this video we are on page 4 of the note packet and we're going to be looking more closely at vector operations today. So we briefly talked about that on the previous page, showing how if I want to see how two vectors affect each other, we can add them tail to head, and then join the initial tail with the final head to get a resultant vector. So that is how we illustrate what is going on, but to do it mathematically and find the sum or the resultant vector, how we do it is by adding the components. So if this is my first vector with components A1 and B1, and this is my second vector with components A2 and B2, we would add the A components to get my resultant A component and my B components to get my resultant B component. So that is how we add two vectors together. Now to find the product of the scalar K and the vector U, we actually did that on a previous page as well when we were talking about those unit vectors I and J. So if I have a multiplier out in front of a vector, I can distribute it to each of the components and get KA1 and KB1. So to find the product using a scalar, we simply distribute. So we're going to see what both of these look like using these illustrations. So first, for sums, we connect tail to head. Then the result is initial tail to final head. All right, so we're going to go ahead and take a look at this first problem where we've got U plus V. So vector U is -1, 3, and vector V is 4, 7. So if I want to add these two vectors together, we would add the A components and the B components. So I'm going to be showing more work than you probably need to on your homework here, just so you know where these numbers are coming from. So A component from the first vector plus A component from the second vector, and then B component of my first vector plus the B component of my second vector. And so that gives me, for my final component form, or the resultant vector, 3, 10. So this would be the resultant of adding those two vectors together. So if I wanted to show this using an illustration or with a graph, I would first start with graphing vector U, which has an A component of -1 and a B component of 3. So 1, 2, 3. And remember, instead of just being a point, I'm graphing this vector in standard position, so it's going to start at the origin and extend up towards that point with an arrow. So there's vector U. Then for vector V, forward 4, 1, 2, 3, 4 for the A component, and up 3, 4, 5, 6, 7 for the B component. So extending to that point from the origin, that is vector V. So if I want to find the sum, similar to what we did on the previous page, we want to connect tail to head. So I'm going to start by moving the blue tail to the pink head, which gets me something about like this. Then to find the result, we take the initial tail here with the final head up here. And that gives me my resultant vector. Does it look like this has the component form of 3, 10? So a little bit slightly to the left of 4 and up 10. So it's not perfect because my scale is not exactly right, but we can definitely see that our resultant vector is in quadrant 1. So connect tail to head, and then our result is the initial tail connected to the final head. And remember, folks, I chose to slide the blue vector up. If I wanted to slide the pink vector, I could slide that tail up to that head And as you can see here, yep, that would extend that green one a little bit taller. So again, not a perfect graph here. And that's about where that resultant vector would be. So you can do it either way, just so long as you are connecting tails to heads. Now, looking at B, if I wanted to multiply 3 times u, I would take that scalar 3, and I would distribute it to both components of vector u. So -1, 3. Distribute, and that gives me -3, 9 for my resultant vector. Now for a scalar product, what this does is it lengthens both the A component and the B component of the vector, making it a longer vector. So here's vector u, so -1, 1, 2, 3. And then -3, 9 would be out here, and 3, 4, 5, up here somewhere. So as you can see, what this has done is it's given me a longer A component and a taller B component, and it has tripled the magnitude of the vector. Let's go ahead and move to our next problem where we have a combination of operations using 2 different vectors. So first I'm going to multiply 2 times vector u, -1, 3, and then add that to -1 times vector v, 4, 7. So again, just distribution, but do make sure you're using the proper notation for vectors. Don't get lazy and accidentally use parentheses. So this gives me -2, 6. This gives me -4, -7. So then when I add these 2 vectors together, we add the A components and the B components, and that gives me -6, -1 for my final answer. Now, it's important to realize that in these problems, we are adding vectors. We are adding their A components and we are adding their B components. In the next section, we are going to be looking at kind of structure of vectors that are floating somewhere in space given certain coordinates. So earlier in the chapter, I had shown you this diagram that shows 3 different vectors that are made from different coordinates, but all have the same component form. So using these 2 points extending from this one to this one, using these 2 points extending from that one to that one, the A component and the B component are the same for all 3 of those. So what we're going to be doing is taking a vector floating somewhere in the coordinate plane, and we are going to find the component form so that it would allow us to put it in that standard position. So the tricky thing about this is the formula and visualizing what is happening. So the magnitude and direction between any 2 points can be represented with a vector, an arrow with the initial point, x1, y1, and a terminal point represents the vector. So first, I just want to draw what this vocab looks like. If this was my initial point, and the vector looks like this with an arrow on that side, then this would be the terminal point. Now, to find the vector between 2 points, and I would highlight this, maybe in a different color of highlighter than you have been using so far, because this is the formula that normally trips people up. This is how we find a vector between 2 points. So we are going to take the x values difference and the y values difference, which is kind of similar to what we've done with slope in the past. However, the order of the points matters. So I want you to write memorize by this, and that the terminal values are first. And if you're wondering, well, why does order matter here? Folks, if I switch the order around, Then what we'd find using the component form is that my arrow would be pointing down instead of pointing up. And this would affect the direction angle because instead of being in quadrant 1, this would be pointing down to quadrant 3 in standard position. So the order matters when you are carrying out this formula for finding a vector between 2 points. So it's easy to get this mixed up to what we were doing with vector operations, but this is adding components of vectors. This is finding a vector between 2 points. So we're going to go ahead and look at this first example, and I'm going to try to help you visualize and carry out the operations here. So it says write vectors v and u in component form. So component form being A, B, where V is RS and U is PQ. So this is a new vector notation that we use when we are drawing a vector between 2 points. So here is point R, here is point S. Because the arrow above the points extends from R to S, what this means is R is the initial point, and S would have the arrow going to it, would be the terminal point. So when we go to use those 2 points to find the equation of the vector, or to find, the standard form for the vector, we're going to need to make sure that we put it in the correct order. So the first thing that I'm going to do is I'm going to plot the points. -4, 2, and -1, 6 to get a visualization of what is going on in this diagram. So I'm going to go ahead and draw my coordinate plane. -4, 2, 1, 2, 3, 4, 1, 2. All right, so there's R, which is my initial point. So I should probably make that green. And then S would be my terminal point. So -1, 6. 1, 2, 3, 4, 5, 6. So that's point S. So that vector looks like this. So you could, if you wanted to, just count visually and say, how many units am I moving to the right for the A component? I'm moving in the positive direction. How many units am I moving up for the B component? In the positive direction. So you could figure it out graphically. So how much am I moving to go from -4 to -1? We'd be moving 3 units. How many units do I move from 2 to 6? 4 units. So I can tell visually that the component form for this vector should be 3, 4. But we're going to go ahead and use this formula so you can see what it looks like algebraically as well. So if I wanted to find my vector V, which is the same as the vector between points R to S, then I would use my vector notation. So this is what can be confusing. It's the vector between these points, so I need to use the vector notation of the terminal points X value, which would be -1, and then minus the initial points X value, which would be -4. Then the terminal points Y value, 6, minus the initial points Y value, 2. And that's going to give me +4 minus 1 is 3, and 6 minus 2 is 4. And that gives me the component form 3, 4. So what this means is if I were to put this vector in standard position, we could start at 0, 0, and go forward 3, up 4, 1, 2, 3, 4. And the vector would be exactly the same. So yeah, my graph isn't perfect, but does this look like it has roughly the same angle and roughly the same length? Yes, so this would be my vector in component form in standard position. So let's go ahead and look at the next one. So my second vector is made up of these 2 points. So vector u, I'm going to go ahead and draw a little line here so we can separate our work. Vector u, which starts at P and goes to Q. So P is the initial, Q is the terminal, then to find the component form for the vector, we would do the x value of the terminal, 5, minus the x value of the initial, 2. Then we would do the y value of the terminal point, and then minus a -1, the y value of the initial. And what we find is that this has the exact same component form as the other vector. So again, folks, vectors, location does not matter when it comes to component form, when we're just looking at those horizontal and vertical components. So if I went to graph those points just to check myself here, P would be at 2, -1. And Q would be at 5, 3. As we can see, that has the same structure and angle as the other vectors. So both of them can be represented by that component form 3, 4. So folks, again, terminal values come first, and then we subtract the initial points, x and y values. So not to be confused with vector operation, this is all dealing with the points that make up a vector. So looking at B, it says find the magnitude and direction of a vector from P to Q. So magnitude and direction of a vector from P to Q, where P is -3, 4, and Q is -5, 2. So from P to Q means that P is the initial point and Q is the terminal point. So folks, I'm going to go ahead and start with graphing those points. So -3, 4, 1, 2, 3, 1, 2, 3, 4. There's P, and then Q is -5, 2. So 3, 4, 5, 2. So what do we know about this vector? So its A component is going backwards. So A is probably going to be negative, and B is going to be negative as well. And the other way I can determine that is if I slide that so that the initial point is in standard position, I'm going to be looking at a vector like this with a -A and a -B value down in quadrant 3. And that will eventually help me find the direction angle, which will also be in quadrant 3. So let's start by finding the vector itself. So we want to find those A and B components using the 2 points. So we do our formula, and I'm going to name this vector PQ with the arrow above it. And this is going to be equal to the terminal x value minus the initial x value. So -5 minus a -3. And then the terminal point's y value minus the initial one. So then, carrying out this operation, we get -2, and we get -2. And notice that I am using that vector notation around that because we have just found the A and B components. Now, does that seem reasonable? Yeah, because our A value is negative and our B value is negative, and it matches with what our vector is showing with going down to quadrant 3. So this is the component form. And it's important that we find the component form first because then I can find the magnitude and the direction. So if I wanted to find the magnitude of PQ, first I would denote that as such. Absolute value bars around the vector. And this is equal to the square root of, how do I find magnitude? A squared plus B squared underneath the square root. So this would be the square root of -2 squared plus -2 squared, which is going to be equal to 4 plus 4 is 8. And don't leave it as the square root of 8. This simplifies to be 2 rad 2. So that is what my magnitude is. And folks, sometimes, excuse me, people will write the arrow like this with just kind of one little tail on it for the notation. Just saves you the slightest bit of time. But if you see that, it still means vector notation. So there's our magnitude. So then to find the direction, we are going to do -b over a. So probably have noticed that that's going to give me the reference angle, but to find the full quadrant 3 angle, we'll probably have to add 180. So tangent of theta is equal to b over a, so working on memorizing those formulas, which is -2 over -2. So, hey, where is tangent equal to 1 in quadrant 1 and in quadrant 3? But we don't want the quadrant 1 angle. It needs to be the quadrant 3 angle. So you actually might be able to figure out that that is 225 without even pulling out your calculator. But if you're having a Monday, me who can't seem to find my red pen, there it is. You can do inverse tangent. And what you'll find is that your calculator is going to tell you that this is 45 degrees. And this is why, folks, I still like to emphasize drawing a diagram and drawing a picture because that will help you remember the quadrant. So 45 degrees is the size of my reference angle, that little wedge in there. So to find a quadrant 3 angle, we're going to need to add 180. And that gives me 225 degrees, which is indeed a quadrant 3 angle. So we've got vector operations by adding, vector operations using scalar products, and then how we find a vector that is between 2 points. Now, what we're going to be getting into in the next part of the chapter is story problems involving finding resultant vectors using these setups and adding the vectors tail to head. Now, folks, we're going to work on the visualization of it, and we're also going to look at the math side of it, but I can't emphasize enough the importance of the diagrams. So, folks, if I have this airplane and the propeller is set to move in this direction at that longer speed, and then I've got a slight wind, so a smaller vector, moving in this direction. What happens when we join that tail to head for the propeller of the plane, tail to head for the wind, the resultant vector of what the airplane is actually doing is initial tail to final head. So that would be the resultant. So the airplane is set to move given this direction of the propeller, but what it is actually doing is affected by the wind. So the wind not only blows it slightly off course, changing the direction angle, but notice that that green resultant vector is also a little bit shorter. So these interacting vectors with different magnitudes and different direction angles have an impact on each other when we add them together. So that concludes page 4 of the notes.